In today's video, we're going to discuss acids and bases and their reactions. So on this slide, we can see soda in a glass, and the soda contains phosphoric acid and carbonic acid, and that's true of most sodas. Now, that might sound kind of scary. Now, phosphoric acid is actually not that bad for you unless you are drinking copious amounts of soda. So phosphate's actually pretty important in terms of the health of your teeth and your bones. But if you consume too much of it, it can actually start to wear away at your teeth and bones. So it can start to break them down. Carbonic acid, that actually decomposes into carbon dioxide and water. So that's not so bad. But we're going to talk a little bit more about some of the reactions that acids can perform. But first, let's talk about what an acid actually is. So we're going to use what's called the Arrhenius definition of an acid. So there's other definitions which you'll probably learn more about in general chemistry. But for now, we're just going to focus on this definition. And this is just named after a scientist, Arrhenius. So Arrhenius acids produce hydrogen ions when they dissolve in water. So a really good example is hydrochloric acid. And when that is dissolved in water, it breaks apart into hydrogen ions and chloride ions. And so all acids are going to produce these hydrogen ions in water. Now we can also call these acids electrolytes. So you might have heard of electrolytes. So for instance, Gatorade constantly talks about how many electrolytes is in the beverage. So electrolytes are really just ions that can produce a current in water. So for instance, potassium ions are electrolytes, sodium ions are electrolytes, nitrate, phosphate, sulfate, all those different ions are electrolytes. And if you look on the label of a Gatorade bottle, it lists different ionic compounds. So they do contain electrolytes. Now, some of those electrolytes are important for cellular function, etc. But Gatorade also contains a lot of sugar, so you have to be careful with how much you ingest. So some other properties of acids, they have a sour taste. So for instance, lemons and limes contain citric acid. And that's what gives it their sour taste. And then also there's what's called litmus paper. And litmus paper can help you determine whether something is acidic or basic by changing color. So with an acid, litmus paper will turn red. And we'll talk more about that later. Additionally, acids can also corrode certain metals. So there are some metals that aren't affected by acids, like silver and gold, but most metals can be broken down with acids. So let's talk about how to name acids. So we already mentioned hydrochloric acid. So this is an acid that has a hydrogen ion and a non-metal. So we would actually call that a binary acid because it only has two components to it, the hydrogen ion and the non-metal. So you would name this by using a prefix, hydro, and then you're going to use the first syllable of the non-metal followed by ic acid. So if we made our little boxes here, we would use the prefix hydro plus the first syllable of the nonmetal plus ic acid. All right. So that's not too bad. Now, if you have an acid with a hydrogen ion and a polyatomic ion, that's where it can be a little more difficult. So we call these oxyacids because most polyatomic ions contain oxygen. So they're oxyacids. All right, so let's say you have an acid where there's a hydrogen ion bonded to a polyatomic ion that ends in ATE. So ClO3 is called chlorate. So if the ending is ATE, we're going to name the acid using the first part of the polyatomic ion name, followed by ic acid. Now, what if the ending is ITE? So let's say instead of ClO3, we have ClO2. This would be chlorite. So if your ending is ITE, then you use US acid, OUS acid. So HClO3 we said was chloric acid, but HClO2 is chlorous acid. So that can be a little more complex when you're naming these acids. So again, you have your binary acids where you use the prefix hydro, and then you have your oxyacids. You're not using a prefix at all. You're just using the first part of the polyatomic ion name, followed by an ending, and the ending will depend on whether your polyatomic ion name ends in ATE or ITE. So that can be a little more complex. So let's look at some examples. So in your textbook, there's a table 11.1, and you'll notice that the first few of these acids contain a halogen, or CN, which is cyanide. Now, all of those acids start with the prefix hydro. Hydro, 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 etc. So these are all hydro followed by the nonmetal name or the cyanide. And the ending is ic acid. So we have hydrofluoric acid, hydrochloric, hydrobromic, hydroiodic, and hydrocyanic acids. Now, the rest of these acids all have polyatomic ions. So the first one here has NO3, nitrate. So the ending for that is ATE. So we would call this nitric acid. And then the next one is HNO2. So instead of NO3, we have NO2. So NO2 is nitrite. So that means this would be nitrous acid. All right, and then we can continue going down the list. So we have in the next row H2SO4. So this acid actually has two hydrogens in it. So that can happen where you have more than one hydrogen ion attached to your polyatomic ion. And mostly that's just to balance the charge because sulfate has a 2- charge. So we need two hydrogen ions to balance it out. So in this case, we have sulfate as our polyatomic ion. So the ending for this acid name would be sulfuric acid. Now, what if we have SO3 instead of SO4? That is sulfite, so we would name that sulfurous acid. And the trend continues going down the list. All right. Now, one acid that you've probably come across a lot is acetic acid, where that has the acetate ion bonded to a hydrogen ion. So acetic acid is what's found in vinegar. And in fact, acetic acid is really good at killing, for instance, mold. I had some mold pop up in my house this winter because we had the wettest January in history or something. And I just used some white vinegar and it cleared it right up. So acetic acid is pretty awesome at that. All right, anyway, so let's do a learning check. So let's select the correct name for each of the following acids. So how would we name HBr? Would that be bromic acid, bromous acid, or hydrobromic acid? So remember, if you have a hydrogen ion bonded to a single non-metal, you have to use the prefix hydro. So this would be hydrobromic acid. All right, what about the next one, H2CO3? Is this carbonic acid, hydrocarbonic acid, or carbonous acid? All right, so let's do a process of elimination. So in this acid, we have CO3, which is a polyatomic ion. So we don't have a single nonmetal, and this also isn't cyanide, which is the other binary acid. So we don't use the prefix hydro here. So this is one of our oxy acids. Okay, so then it's down to carbonic acid or carbonous acid. So how do we name that polyatomic ion, CO3? So this is carbonate. So it ends in ATE. So would we end this in ic acid or us acid? Ic acid. So we would use ic acid as our ending there. All right, and then last but not least, we have HBrO2. Okay, so this one's a little tricky. So BrO2 is our polyatomic ion. And is this an oxy acid or a binary acid? So this is an oxy acid. So we can already eliminate B because we're not going to use the prefix hydro. So now it just comes down to the ending. Do we use ic acid or us acid? So this is probably a more difficult polyatomic ion to remember the name of, but this would be the bromite ion. So this ends in ITE. So this would be something you might have to look up in a table, for instance. Okay, but if the ending is ITE, would the acid name end in ic or us? Us. So this would be bromous acid. Okay, so hopefully that helps a little bit with figuring out how to name acids. And this will come up again in general chemistry as well. Okay. So now let's talk about bases. So we're going to look at the Arrhenius definition for bases. So bases produce hydroxide ions in water. So a really good example is sodium hydroxide. This is a really strong base, and when sodium hydroxide is added to water, it breaks apart into sodium ions and hydroxide ions. So bases typically taste bitter or chalky. So if you've ever had Tums, Tums contains bases, and so they taste pretty chalky. Bases are also electrolytes because they produce ions in solution. Bases can also feel soapy and slippery. So for instance, if you've ever used bleach to clean your bathroom or your kitchen before, and maybe you accidentally touched it or got it on your fingers, it feels really slippery. Or even like laundry detergent. Laundry detergent has bases in it, and that can feel really slippery and soapy. Now, we talked about litmus paper earlier. So litmus paper again changes color depending on whether it's dipped in a base or an acid. So litmus paper will turn blue if it comes into contact with a base. But again, we'll talk about that a little bit more later. Now, naming bases is so much easier than naming acids. So since bases contain hydroxide ions, we're just going to name everything like we would a regular ionic compound. So for instance, NaOH is just sodium hydroxide, KOH is potassium hydroxide, BaOH2 is barium hydroxide, AlOH3 is aluminum hydroxide. So super easy. You just have to name the metal followed by hydroxide. Now, if you've ever had to have a root canal, they probably were using calcium hydroxide to fill in that root canal, and that's another base, calcium hydroxide. Okay, so let's do a quick learning check. Let's match the formulas of the acids and bases shown below with their names. So if you want to pause the video and try this on your own, you can. And when you unpause the video, we'll go over it together. Okay, so let's start with HNO2. So is that an acid or a base? So it doesn't have OH in it, right? So it's not a base, but it does have a hydrogen ion, so it is an acid. Okay, now let's figure out, is this a binary acid or an oxyacid? So this does have oxygen in it, so it's an oxyacid. Okay, so that's going to help us figure out how to name this. Okay, so if it's an oxyacid, we know that we're not going to use the prefix hydro, and we're just going to name this based on the polyatomic ion. So this is the polyatomic ion nitrite. So then how would we name the acid? This would be nitrous acid, so this would be D. All right, so let's look at the next one. We have calcium bonded to two hydroxide ions. So is this an acid or a base? A base, because we have hydroxide. All right, so how would we name that compound? Calcium hydroxide, so that would be E. All right, let's look at the next one, H2SO4. Is that an acid or a base? So I don't see any hydroxide ions, so this would be an acid, and I do in fact see a couple of hydrogens there. All right, and then since this is an acid, is it a binary acid or an oxyacid? It's an oxyacid. Okay, so we're going to name this based on the polyatomic ion. So which polyatomic ion is SO4? How do we name that? So that is sulfate. So then what is the acid name? B, sulfuric acid. So ic acid. Okay, next we have HiO3. Is that an acid or a base? It's an acid. We don't have OH in it, but we do have a hydrogen there. So this polyatomic ion here is iodate. So it ends in ATE. So how would we name that acid? Well, we only have two options left, right? So it would be iodic acid. And then last but not least, we have NaOH. And there's only one option left, which is sodium hydroxide. Okay. Great. So now let's talk a little bit about the types of reactions that acids can perform. So acids have three main reactions. They can react with metals, and they'll produce a salt and hydrogen gas. And down below we have the definition for a salt. So it's not just sodium chloride, which is our typical table salt. A salt is any ionic compound that does not have a hydrogen ion as the cation or hydroxide as the anion. So it's not an acid or a base, but it is an ionic compound. So we'll see some examples of this in a bit. Now, acids can also react with bases, and in that reaction, they'll produce a salt and water. And then acids can react with bicarbonate and carbonate ions to produce carbon dioxide gas, but additionally, it will form a salt and water. So remember, carbonate ions are CO3 2-, and then bicarbonate has a hydrogen attached, and it's HCO3-. So that can also be called hydrogen carbonate. Okay, so let's look at these reactions in a little more detail. All right, so acids again can react with metals to produce hydrogen gas, and then the salt of the metal. So for instance, let's look at this first reaction here. So in this reaction, we have magnesium, which is a pure metal, and then it's reacting with hydrochloric acid, and then it's producing magnesium chloride and hydrogen gas. So magnesium chloride is an ionic compound, and it does not contain hydrogen or hydroxide, so that would be considered a salt. All right, and then we have hydrogen gas. And remember, hydrogen is one of our diatomic molecules. So it has to be H2. It's in a pair. And remember the acronym Hofbrinkel. So that can help you remember which of the elements are diatomic. So we have hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine. Now, if we look below at the second example here, we have, instead of magnesium, zinc. And zinc goes through a very similar reaction with hydrochloric acid. But instead of producing magnesium chloride, we produce zinc chloride. And then off to the right, you can see the reaction between magnesium and hydrochloric acid. So we've got a magnesium ribbon here, and it's reacting with hydrochloric acid to produce some bubbles, and those bubbles are hydrogen gas. All right, so now let's look at another type of reaction. Here, acids react with carbonates and bicarbonates, or hydrogen carbonates, and they will produce carbon dioxide, salt, and water. And this is actually going to be the type of reaction you'll see in our lab for the week, so in the carbonates lab. So let's look at the first reaction. We have hydrochloric acid reacting with calcium carbonate to produce carbon dioxide, calcium chloride, and water. Okay, so we have our CO2 gas and then H2O, and then the salt is formed based on what's left over. So we have calcium and chlorine. So if we look at that in a little bit more detail, so if we look at CO3, that's going to give us our CO2 and then our oxygen in H2O. And then from HCl, or the two HCl's there, that will give us the hydrogens in water. And then everything that's left over, so the chlorine and the calcium, will give us our salt. So let's look at the second reaction here. Here we have hydrochloric acid again, and this time it's reacting with sodium bicarbonate. And then that's going to give us very similar products. We have CO2 and H2O, but our salt is different. And again, the salt depends on what's left over. So again, CO3 is going to give us CO2, and one of the oxygens will go to water. And then we have a hydrogen from hydrochloric acid and a hydrogen from our bicarbonate polyatomic ion. And those are going to give us the hydrogens in water. And then finally, what's left over is chlorine and sodium, and that will give us sodium chloride. Okay, and we'll talk about this also in a video for the lab that you're doing this week. All right, so let's talk about the last type of reaction, acids and bases, or acids and hydroxides. So this is also called a neutralization reaction because when acids and bases react together, they end up producing neutral products. So products that aren't acidic or basic. So in a neutralization reaction, an acid reacts with a base to produce salt and water. And the salt that's formed is coming from the anion from the acid and the cation from the base. So down below, we have a reaction between hydrochloric acid and sodium hydroxide. So the hydrogen from the acid and hydroxide from the base are forming H2O, water. And then what's left over is chlorine and sodium, so that makes sodium chloride. Okay, so neutralization reactions aren't too bad. So now, in neutralization reactions, one thing to keep in mind is that one hydrogen ion will always react with one hydroxide ion to make water. So they'll make H2O. So looking at our strong acid and strong base reaction, where we have HCl and NaOH, we can see that the hydrogen and the hydroxide form water, and that just leaves sodium and chloride in solution. So if we write the ionic equation for this reaction, we have H plus, Cl minus, Na plus, and OH minus, and that's going to form Na plus, Cl minus, and H2O. And we're just leaving H2O as a liquid because we're not going to see those bonds break apart. They're not aqueous like the other ions are. So now if we identify the spectator ions, or the ions that don't do anything in solution, we can cancel those. And in this case, that's the sodium ions and the chloride ions. So then we can write out the net ionic equation, which is hydrogen plus OH minus gives us H2O, which is a liquid. All right. Okay, so now let's talk about how to balance neutralization reactions. There's a little trick you can use to balance these types of reactions. So for instance, let's say we have magnesium hydroxide reacting with nitric acid. Now we know that we have an acid and a base, so we know that one of our products will always be liquid water. And then we just have to figure out what is the salt that forms. So first, remember, we have to balance the hydrogen ions with the hydroxide ions, because we just saw that one hydrogen ion reacts with one hydroxide ion to make one water molecule. So in this instance, we have two hydroxide ions, but we only have one hydrogen ion. So we're going to have to put a 2 in front of the acid. So that's shown down below. Okay, so now we have 2 OH minus and 2 H plus. Great. Okay, so how many water molecules can we make from those 2 hydroxides and 2 hydrogen ions? 2, right? So we're going to need to put a 2 in front of H2O in the products. So you'll notice in step 3, we have balanced the acid and the water molecules there. And then we just have to write the salt product from the remaining ions. So if we highlight what we've used to make water, we just have to figure out what's left. So we have magnesium and then 2 nitrate ions. So that will give us magnesium nitrate as our salt. Now, this is just one way to balance neutralization reactions. If you want to do it the way we were balancing reactions before, totally fine. This is just a little trick you can use to balance neutralization reactions. But again, it's just one way to do it. There's so many different ways to balance reactions. So whatever works for you. All right, so let's write a balanced equation for the following reaction. So this time we have magnesium hydroxide and hydrobromic acid. So if you want to try this on your own first, you can pause the video, and then when you unpause, we'll go over it together. All right, so again, according to our previous technique that we just went over, we have 2 hydroxide ions, but only 1 hydrogen ion. Okay, and we know that we're supposed to form a salt and water. So if we know that we're forming a water molecule, first we need to balance the hydrogen ions and the hydroxide ions. So we're going to need 2 hydrobromic acid molecules so that we have 2 hydrogen ions. Okay, so now in the next step, we need to balance the number of water molecules. So if we have 2 hydroxide ions and 2 hydrogen ions, how many water molecules can we make? 2. So that means we need to put a 2 in front of H2O in our products. Okay. So the next step, we have to figure out what is the salt that forms. So we just used our hydroxide ions and hydrogen ions to make water. So what's left over? So we've got magnesium and we have 2 bromide ions. So we've got Mg and then we have 2 bromines. So Mg has a 2+ charge. What's the charge on bromine? -1, and we have 2 of them. So that would make MgBr2. Okay, so our full equation looks like this. So we have 1 magnesium hydroxide compound reacting with 2 hydrobromic acid molecules to give us 1 magnesium bromide compound, which will be aqueous. And then we have 2 water molecules, which are a liquid. Okay. So again, you don't have to do it that way. You could balance this, a different way if you have a different method that you use. All right, and there's the solution slides. So we'll stop there today. Next time we're going to talk about one more type of reaction called an oxidation-reduction reaction. So I've mentioned that if iron reacts with oxygen, it forms rust. That's actually an oxidation-reduction reaction. So we'll talk a little bit more about that in the next video.